Hello guys, it's Ert here, and welcome back to another physics video. So today we'll be talking about dosage, specifically radiation dosage. And in this case, it's more in the medical field, but there is some addition to our notation that we need to cover. So let us first start with just regular old dosage. So dosage is seen here just as units of meters squared per second squared. And it is usually defined as the energy per mass, which means that, well, you can kind of see we have kilograms meters squared per second squared, and we've divided by kilograms. So that just leaves us with meters squared per second squared. Let us now look at the equivalent dose. The equivalent dose, usually symbolized by H and having the same units as the absorbed dose, is the absorbed dose D summed over the different radiation types. So in the standard notation, that'd be the sum over radiation types, the dose by radiation types, and we will actually instead denote that by saying that we are summing over the radiation types. That will be our new notation for it. And actually I'll do this above it just to differ it from resistance. This is not a formal part of the notation. Then we can look at the equivalent committed dose, of which I think is symbolized by C. Sadly, I didn't see an actual letter when I did my research. At least I don't remember seeing an actual letter for this, so I just assumed it to be C. But the committed dose is the integral of the dose of a certain kind of radiation per time. And so it has units of meters squared per second, and thus we will use the symbol omega to define this. I believe the symbol has already been defined, but I will define it like that anyways. And then I would like to look at activity. And activity is the number of particle transformations per second. And usually we would see this as Vn, but I wanted slightly better units instead of just frequency. And we can see that one transformation is a change in entropy, well, a very small change in entropy. And entropy is just F2T. Or I will also allow ft squared. So we can label activity as being the change in entropy, or the number of changes in entropy per second, basically. And this will be our notation for this because sadly we don't have our own unit for entropy. So we will formalize this notation later on in the episode. So now I will look at the effective dose. The effective dose is the weighted sum of the dose by radiation type and tissue type, and we are only looking at the mathematical side of things here. But it's also weighted by a radiation and a tissue. And thus it is a dosage with an average or weighted sum by radiation and by tissue. And then we can look at the collective dose, of which is symbolized by S. And it is the sum of effective doses over the time that they occurred in. And thus we have summed over the radiation and tissue. And now we are summing over time. And now I would like to check out the exposure. And exposure has units of kilograms per coulomb. And luckily, we do have a symbol for this. And this is mu by charge. This reminds us of another concept that we've seen earlier in the series, which is permeance. And interestingly, the only thing that changes here is that permeance was this. So it's kilograms meters per coulomb squared, I believe. and that was mu 1q, where this is mu 0q. I would like to look at the committed effective dose. The committed effective dose is the sum of doses with a radiation type R and a tissue type T. And it is averaged over the tissue type and just summed over the radiation type. Actually, that's the main symbol, so that's spoilers. But the definition is the sum over the committed doses. Sum over the committed doses by tissue type, weighted by the tissue type. And this is actually the wrong letter because it is supposed to be omega. And that is actually the sum over R. I am sorry I don't have that written down. So then let us look at the new notations that we have come up with. Firstly, we have come up with something summed over a bunch of objects. So that is just sum over K. This is just a new notation for this. So XK. And then we can also get an averaged object. And this just uses the plus minus symbol. And this is just a sum over K of a weight, K and XK. And of course, this can also mean an average. So this weight can just be the number of X's. And that works at, 1 over the number of X's. And that can be considered an average. And then I would finally like to add one extra piece of notation to this. That is x plus to the n k. And this is just the nth root of the sum over k of xk to the n. And the way this is useful is, say, with impedance. Impedance, which in regular notation is z. That is just the sum of the resistance from the capacitor and the resistance from the inductor squared. That was horribly explained, but pretty well written. And I know these usually use different symbols because they aren't necessarily actual resistances, but they have resistance units, and so we're using resistance. But this will now become the resistance plus squared per the elements, which will be capacitance and inductance, of which is just mass. So that is how you would write that in the new notation. Or you could really just write that you got it from capacitance and inductance, like that, and then just do this. And there you go. And then I would like to look at one last addition. And we have already shown that dosage is an energy per mass. So let's generalize that to a much bigger amount of objects. So here is the very huge formula. And basically, speed of light squared. The cedilla here just makes it a constant. That's all it does. So for example, we have Avogadro's number. Well, we will look at Avogadro's number later. All the cedilla does is separate it from being unitless so that we can still have the usual constants. And then we can look at the rest of this whole mess equation. This is the sum over all particles in the area that we're summing over. Well, volume that we're summing over. That is the sum of all particles of the mass of the particle times the exponential of a transformed version of the particle's spin plus the charge of the particle. So if we are looking at just everyday objects, like say we were counting coins, or maybe not cars because that's a little bit more advanced, but you could theoretically do this for cars. So now we will look at how to turn this into a general volume or a general object. Because this object right here is the sum of all particles within a system, and as you can see, this top part has units of, well, this part is unitless, so it just has units of joules, which is kilograms per meter squared per second squared, and this just says units of mass. This is messy and it's pretty hard to compute, so I've found a formula that's easier to compute for larger volumes. So all of the base particles, that is protons, electrons, and neutrons, that are in the base atom or base molecule can be counted within that molecule. And of course, a mole is defined as a specific number of particles. So we first look at how many of this molecule are in the volume that we're specifying. And well, that's easy to count. So first, Avogadro's number is the number of particles within a mole, and the number of moles per volume is the molar volume, of which is A3 eta. And I need to move this downwards a little bit. And so now that we have that, we have just found the number of molecules per a volume. And I will prove that by showing the units. We have officially found that. Now that we've done that, all we have to do is multiply by the volume. And thus, we have just officially found the number of molecules within this volume just by doing this formula. This is quite simple and quite neat. However, we're not done yet because we want to count the individual particles. Luckily, this formula is pretty easy to evaluate from the formula up top. And so what we can do is we can sum over each molecule type and find the number of protons within that molecule, which I will write a little higher actually. Number of protons within the molecule times the mass of a proton times E. We will evaluate this part soon. Plus number of neutrons times the mass of the neutron, plus number of electrons times the mass of the electron, times E inverse. So there we go. And then in order to include the angular momentum, this includes the charge. In order to do the exponential for the angular momentum, luckily protons, neutrons, and electrons all have the same spin. So outside of the sum, we can just write e to the I h over 2. I pi h over 2. There we go. We have just found that entire spin, and all that's left now is to multiply by c squared and divide by the masses of each particle in the molecule. That is the complete formula. We have now found a way to create a dosage of an object. Actually, I need to zoom out a bit to allow the full formula to fit in. And so, I would first like to look at the E's and E inverses. And we'll also note that here, e to the 0 is 1, and neutrons have 0 charge. So 0 over any charge is just 0. Now, the charge of the proton over itself is just 1, so we get e to the 1. And the charge of the electron is the exact negative of the charge of the proton, so that just equals -1, so e to the -1 comes out here. Then all we have left is to look at the spin. After some research, I found that the neutron, electron, and proton have the exact same spin. And so, if I mark things out, this will always be the exact same, no matter which particle you're doing, proton, electron, neutron. Now, of course, if you're doing one of the smaller particles, that would be maybe a quark or something else, you would probably need to modify this. But for a normal particle, that is all that counts. Now that we have the dosage of this object, we can also do another form where we may need to replace volume with mass, and we may need to replace the molar volume with the reciprocal of molar mass. And thus, we can either define it through mass or volume, so I will write those both here. So you can have dosage of an object by mass, or dosage of an object by volume. Whichever one you favor, or whichever one is easier to compute, is up to you. So the reason why we need this is, let's say we're measuring things from batteries. So we want to measure how many volts are given to a circuit per battery. Well, we usually just do volts per battery like this, but now we can actually have an SI unit attached to it. Specifically, volt per, it would usually be gray if we're talking about radiation, but here we get volts times meter squared per second squared, or we can just do more with this. Now, why in the world would you need this variable? The reason why is so that you could give any object SI units. And specifically, those SI units will always be some scalar multiple of meter squared per second squared. And as you can tell, it will always be complex. And so all that matters is that we have a way to turn any object into SI units. Now, the only other thing I'd like to cover is I want to go back over some of the other notations we've done earlier in the video. So firstly, we've seen C squared, we've seen the Avogadro's number, we've seen R, and all of these I've added a cedilla to show that an object is a constant instead of a variable. I would like to mention a coincidence with Avogadro's number. Because it has units of mole inverse, or 1 per mole, the letter for that is nu, so it'd be nu eta. And the capital of nu is just N. So it's still the same notation. Earlier in the video, I showed something like this. It was actually V of ft squared, I'm sorry. And this was in reference to entropy. Now, the reason I'm making this allowability in notation is because, well, let's just do it normally, and you'll see that there's this string of underscores, which I don't like. And somehow in LaTeX, it works very well to have a superscript or an exponent in a subscript. So that's what I've done. Now, another thing I would like to look at is some extensions to our sum rule. So we've already seen x plus n is the sum over all n of x sub n. And of course, I would also like to add a weight to it. But I can also do both versions at the same time, which means I can put it to a negative power, and I would actually like to raise that to the k, and put that to the 1 over kth root, and there is the definition of the entire sum rule. And I would like to mention with this, actually up here, this is wrong. This is supposed to be a plus minus because it is an average. And so that is it for this video. So with that being said, this has been Ert, and I will see you all in the next video. Goodbye for now, and peace.